So I want you to picture this. You are standing in the middle of a manufacturing facility. And we're not talking about some messy, chaotic workshop here.
Right, no oil spills on the floor.
Exactly. Not a haphazard pile of scrap metal anywhere in sight. I mean, this is an immaculate, highly restrained, incredibly precise production environment.
The kind of place where, every single tool has a designated shadow board on the wall.
Oh, yeah. The floors are that spotless concrete gray. There's got the bright yellow safety lines everywhere. And the ambient air just, like, hums with the quiet efficiency of modern industry.
You can almost smell it, right? That faint, clean scent of cutting fluid and ozone.
Yes. And right there, sitting squarely at the center of your field of vision, positioned awkwardly between two of these advanced multi-million-dollar manufacturing cells, is this simple four-wheeled industrial trolley.
And honestly, it is the most mundane object in the room. Just a standard, unassuming steel trolley with, rubber casters.
So what's resting on top of it is quite striking, really.
Yeah, it's one beautifully machined, precisely manufactured component.
I mean, even to an untrained eye, this thing looks incredibly valuable. It gleams under those soft, color-corrected LED panels on the factory ceiling.
You can tell just by looking at it, right? The complex geometry of the metal, the intricate threading.
The flawless surface finish.
Yeah.
Like, it has already consumed a massive amount of labor, high-grade exotic material, and just sheer electrical energy to get to this point.
And there's this modest little routing card attached to it with a wire tie.
Right. And if you lean in to read it, you see this long, heavily stamped list of completed operational stages. Like milling is checked off. Lasing checked off.
Surface treatment, thermal induction, intermediate quality inspection, all checked, initialed, and dated.
But right at the very bottom of that card, there is one blank final stage.
Which means, despite looking incredibly sophisticated and, highly polished and thoroughly processed, that component cannot be shipped to a customer.
It can't be sold.
No. It cannot be installed into the final assembly. It is just trapped, literally inches from the finish line.
And here is the absolute punchline to this whole scene. You look down at the floor beneath the trolley. There's this professionally printed, laminated, high-visibility yellow floor sign that reads, "Temporary work in process."
But if you look really closely at the concrete right around that sign...
Oh, man. You see subtle, heavy floor wear. The sealant is rubbed away.
The concrete is discolored.
Yeah, it's the kind of wear that only happens when a supposed temporary cart has sat in the exact same spot, being bumped by passing forklifts and swept around by the janitorial staff for a very, very long time.
It's just this profound organizational contradiction. I mean, you are looking at an object of immense engineering effort and financial investment frozen in a state of administrative and physical limbo.
But if most of the work is already complete, why is this the expensive part?
Because most of the cost has arrived. The value hasn't.
Right. And that tension, that exact contradiction between cost arriving and value being delayed, is the entire mission of today's deep dive.
We are taking a comprehensive look at a fascinating set of operational principles laid out in our primary source material for today, which is this document known as Field Note number 008.
Yeah, we're going to deconstruct the illusion of activity. Because the goal over our time together is to help you, whether you manage a factory floor or lead a software development team or, honestly, just try to survive a flooded corporate email inbox.
Which is all of us, really.
Right. We want to help you recognize how unfinished work is actually a committed investment just waiting to become usable value.
We're going to look at the physics of how work flows, or I guess more often how it stalls, and why our human instincts about productivity are just often mathematically wrong.
It requires a massive paradigm shift. Because, we are deeply conditioned by our culture and by traditional management theory to look at high levels of activity and just assume it equals progress.
Exactly. And we look at a machine running at top speed, or a team working overtime, or an almost finished product on a trolley, and we feel this sense of accomplishment. We think, wow, look at all this work getting done.
But we need to rigorously deconstruct that illusion today. Because a nearly finished product is not an operational asset.
No. Until it crosses the final finish line, until it's actually in the hands of the customer, fulfilling its intended purpose, it is fundamentally a financial and operational liability.
Well, let's unpack the economics of that, because my initial instinct, looking at that beautiful component on the trolley, is to feel pretty good about it.
Right. It looks impressive.
It does. I want to argue from a traditional accounting perspective here. Like, if I'm the chief financial officer walking the floor, I look at that cart and I think, this is great. We've built up our inventory. We are extremely prepared for future orders.
Sure.
I mean, on our balance sheet, that unfinished component is literally listed under current assets. It adds to the book value of the company. So how is that a liability?
Well, that is the traditional financial accounting view, and it's exactly what makes this situation so deceptive and really so dangerous for organizations.
How so?
Because GAAP accounting, generally accepted accounting principles, allows you to capitalize the costs of manufacturing into inventory. So on paper, wealth hasn't been destroyed. It has merely changed forms from cash to an asset.
Okay, that makes sense on a spreadsheet.
Right. But we have to shift our perspective from pure financial accounting to systemic operations. Operationally, what can you actually do with that component today?
Honestly, nothing. I can't do anything with it.
Exactly. You cannot ship it to a client.
Yeah.
You cannot use it to satisfy a customer's urgent need. You can't trigger a final invoice and actually collect real cash revenue merely by having a highly polished piece of metal looking extremely prepared next to a faded yellow floor marking.
Yeah, the accounting ledger might call it an asset, but the operational reality is that it's a barricade. So to really understand the burden it represents, we have to catalog exactly what this perfectly ordinary component have already consumed from the organization. Like, let's trace it back.
It is a surprisingly extensive list when you really break down the life cycle of that single part. I mean, before that item even reached the trolley, the organization had to lay out hard capital to purchase the raw material.
Let's say it's aerospace-grade titanium.
Okay, titanium. The purchasing department spent hours sourcing it, right? Negotiating the contract, paying for the freight to get it to the loading dock.
And then the organization paid for the raw electricity, like the actual kilowatt hours, to spin the spindles of the CNC machines that carved it.
And those machines are depreciating with every rotation. The tooling bits, the diamond-tipped cutters, those are all being worn down and will eventually need to be replaced.
Not to mention, they're paying for the highly skilled labor of the machinists who set up the job, monitored the tolerances, and performed the intricate cuts.
Right, and they paid for the quality assurance inspectors who took out their micrometers and spent 30 minutes verifying all the dimensions against the engineering drawings.
And the material handlers who drove the forklift to move the raw billet to the machine and then move the partially finished part to the trolley.
They are even paying a proportional cost for the climate-controlled floor space that the trolley currently occupies, the overhead lighting shining down on it, and the insurance premiums covering the facility.
I see where this is going. All of those things, the money, the time, the electricity, the human effort, they are sunk.
Completely sunk.
They're trapped inside that geometry of metal. They don't politely reverse themselves just because the work has paused.
The material doesn't just magically return to the supplier to be inverted back into cash in your checking account. The machine time that was consumed yesterday does not magically reappear in today's production schedule, so you can use it to build something a customer actually wants today.
The skilled labor hours are gone. Those workers went home, they received their paychecks.
Yeah, the organization has bled out all of these resources, injected them into this item, and now the item just sits there. Financially, it represents a massive non-liquid commitment.
Operationally, it is simply waiting.
It is an organization's investment indefinitely paused in a twilight zone between cost and value. Almost finished is where cost waits for completion.
Almost finished is where cost waits for completion.
Mm.
That is a heavy realization. I mean, it flips the script entirely.
It does.
It means the organization has paid for 99% of the effort, absorbed 100% of the risk, but received absolutely 0% of the reward.
And because our accounting systems tell us it's an asset, and because our eyes tell us it looks like hard work, we don't view it as massive liability. Therefore, we just allow the waiting to escalate. We normalize the stall.
I have seen this happen in real time.
Yeah.
I mean, it starts incredibly small, almost innocently. You have an operator running a machine, and the next machine in the sequence is down for, say, a 15-minute maintenance check.
Right, very standard.
So the operator finishes 3 parts and just sets them gently on the edge of the workbench. You walk by and think, oh, it's just a tiny buffer. It's a temporary hiccup. No big deal.
But then the maintenance check takes longer than expected, or the downstream machine runs slightly slower on the next batch. So by next week, there are 12 parts sitting there.
And 12 parts are far too many to just leave scattered on a workbench. It's a safety hazard. It looks messy.
So someone, trying to be helpful and organized, goes to the supply closet and finds a trolley. They neatly stack the 12 parts on the trolley.
Now, they have been legitimized. They are officially on a piece of transport equipment, But, a trolley is a mobile hazard if left in the aisle, so the trolley needs somewhere safe to go.
Naturally, it gets pushed into a small, unused footprint between two columns.
And nature abhors a vacuum, but factory managers abhor undefined space. So the next time the facility manager walks by, they see a trolley sitting in an unmarked area. They don't ask why the parts aren't finished. They ask why the floor isn't marked.
Yes, exactly. So they get out the yellow floor tape, and that parking space receives a brightly painted outline and a location number, like staging area 4B.
Now it's part of the facility's geography. And because it has a location number, that number must enter a spreadsheet for inventory tracking.
And suddenly, an administrative clerk is updating that spreadsheet every single morning at 8 a.m. with extraordinary punctuality, noting that the 12 parts are still sitting in staging area 4B.
The system adapts to the dysfunction. The anomaly becomes completely structural. The organization has built a permanent infrastructure to house a temporary problem.
And this brings into focus a vital distinction we really have to make when analyzing any system of work, which is the profound difference between movement and progress. Because once that spreadsheet exists, once that painted square exists, people begin tracking the status of the item.
Right.
And status tracking creates a very seductive mirage of forward momentum.
Yeah, if I am the manager defending my department, I might look at that component on the cart and argue, hey, this isn't a failure. Things are happening to it. It's active in our system.
You'd have the paperwork to prove it.
Exactly. I could pull up the enterprise software and show you that its status changed from Station 4 complete to in transit to queue staging area 4B. A supervisor physically walked over with the tablet and signed off on the transfer protocol.
A forklift driver might have even physically wheeled the cart from the north side of the factory to the south side to make room for a new machine installation.
Right, so there's undeniable activity surrounding this object.
But we must rigorously differentiate between an administrative status change and a genuine operational transformation. Because an item can be moved 20 meters across a factory floor, it can have its barcode scanned 5 times, it can be the subject of 3 different email threads without moving 1 single minute closer to actual delivery.
It's the illusion of activity. It feels like work is getting done because human beings are expending calories and burning cognitive load, managing the stalled work. We mistake our own exhaustion for productivity.
Well said. Physical or administrative motion photographs really well. If you take a snapshot of a forklift moving a cart or a manager typing an email about a delayed part, it looks like a productive company.
It really does.
But actual completion, the physical or digital transformation of the product into something closer to its final valuable state that is much less easily impersonated. Motion is easy to fake. Transformation is not.
The work moved from pending to under review. Operationally, nothing happened. Administratively, it had quite a journey.
It's delivered as a dry joke, but anyone who has worked in a large organization feels the painful accuracy of that statement.
Oh, definitely.
We build these vast, towering administrative architectures, committees, review boards, compliance checks, status meetings, all to govern things that are fundamentally just standing still. We curate the waiting.
So the fundamental diagnostic question you must ask when looking at any piece of work in any system is this. Is this work progressing toward completion or merely changing location?
Are we transforming the molecular structure of the metal, or are we just rearranging the furniture on the shop floor?
Are we writing code that a user will experience today, or are we just moving a digital ticket from one column on a screen to another? And, that leads us to a massive systemic trap, because we have to ask why. Why do these carts of unfinished work pile up in the first place?
Why do rational, intelligent managers allow it to happen?
Right. And it almost always comes down to how we define and measure efficiency, specifically the danger of local efficiency.
Local optimization is perhaps the most destructive force in modern operations management.
Let me set up a scenario that I think every business leader can relate to. Let's say I'm the factory manager. I have a capital expenditure budget, and I just used it to buy a state-of-the-art $1 million piece of upstream machinery. It is a marvel of modern engineering. It cuts metal twice as fast as our old machines. Now, traditional management theory, and frankly my own common sense, tells me that if I spend $1 million on an asset, I need to extract a return on that investment.
Of course.
I need to run that machine constantly across 3 shifts, never letting it sit idle. An idle $1 million machine feels like a terrible, unforgivable waste of corporate resources.
It absolutely feels like a waste and this is the critical caveat, If you are only looking at that one machine in isolation,
Yeah.
if you draw a tight imaginary box around that single piece of equipment, then yeah, maximizing its output seems like the logical goal. But this is where the source material introduces the theory of constraints.
Oh, right.
It's a management philosophy originally developed by Dr. Eliyahu Goldratt in his seminal book, The Goal. And the theory of constraints completely shatters that localized, isolated way of thinking.
Okay, I've heard of Goldratt, but let's really break down the core mechanics of what he was arguing, because it feels deeply counterintuitive at first glance.
His core idea is deceptively simple, yet it redefines how you view a business. He stated that every complex system, no matter what it does, whether it manufactures car parts or processes insurance claims or develops smartphone apps, it is limited from achieving more of its goal by at least one constraint.
So there's always a bottleneck.
Always. If there wasn't a bottleneck, the system's output would be infinite. And he used a very elegant physical analogy for this. A chain.
Right. A chain is only as strong as its weakest link. We've all heard the cliche, but it's an absolute, undeniable physical reality.
Exactly.
If I am using a heavy-duty chain to tow a broken-down truck out of a ditch, and that chain has 99 links forged from industrial steel that can each hold 10,000 pounds of tension, but there is one single rusted link in the middle that can only hold 2,000 pounds, the absolute maximum towing capacity of that entire chain is exactly 2,000 pounds.
It can't be anything else.
Right. The moment I apply 2,001 pounds of force, the chain snaps at the rusted link. The other 99 links, no matter how strong they are completely irrelevant to the breaking point.
The strength of the chain is entirely dictated by the constraint. Now let us apply traditional local efficiency thinking to that chain. You are the manager of the chain, you want to improve it,
Naturally.
but you don't focus on the weakest link. Instead, you decide to optimize a non-constraint. Let's say you take one of those 10,000-pound links, you spend a massive amount of capital and engineering effort, and you reinforce it so it can now hold 20,000 pounds.
You double its capacity.
Right. What happens to the overall strength of the entire chain when you go back to tow the truck?
It stays exactly at 2,000 pounds. It doesn't improve by a single ounce. The weakest link didn't change, so the system's output didn't change.
Precisely. Strengthening a non-constraint does not increase the overall strength of the system. In fact, Goldratt pointed out something even more insidious.
What's that?
By optimizing a non-constraint, you might actually decrease the overall effectiveness of the system. Because what have you really done? You have added unnecessary weight, bulk, and cost to the chain without improving its performance.
Wow, yeah. You made the chain heavier and more expensive to drag around, but it still breaks at 2,000 pounds.
Exactly. So if we map that chain analogy directly back to your factory floor, your new $1 million lightning-fast machine is one of those 10,000-pound links.
Let's assume my new machine is an upstream process occurring early in the manufacturing sequence, and crucially, it is not the system's bottleneck.
Right. Let's say the true bottleneck is the downstream process right after it. Maybe a highly complex manual inspection station or like a slow thermal curing oven.
But I'm the manager. I want my ROI, and my personal performance bonus is tied to equipment utilization metrics. So I tell the operators, run that new machine at 100% capacity. Feed it raw material as fast as it can eat.
And the machine does exactly what it was engineered to do. It produces parts incredibly fast. Its localized utilization metric goes through the roof. On the executive dashboard, the light next to that machine turns a bright, reassuring green.
The manager in charge of that specific department is celebrated for achieving record-breaking efficiency.
But wait, the downstream inspection station, the rusted link holding 2,000 pounds, it can't physically absorb all those parts? It hasn't gotten any faster.
No, it hasn't. It processes parts at its exact same slow, constrained pace. So what is the inevitable physical result? The output of my incredibly fast, highly optimized $1 million machine simply piles up in a massive, growing mountain of inventory directly in front of the slow inspection station.
It's just churning out carts and carts of unfinished work. The fast machine hasn't actually created more finished flow for the entire system because the system's total output is irrevocably capped by the inspection station.
Right.
By running the non-constraint at maximum speed, all your organization has done is manufactures waiting more efficiently.
It manufactures waiting more efficiently. That is such a brutal way to phrase it, but it's undeniable. I have spent $1 million in capital. I am burning through premium raw materials at record speed. I am paying for the electricity to run the machine, all to accomplish nothing more than creating a massive traffic jam on my own factory floor. I am accelerating the rate at which I trap my own cash.
It is one of the most convincing and pervasive illusions in all of business operations. Because if a senior executive walks that factory floor, every single resource appears highly productive.
The machines are loud and humming. Forklifts are zooming back and forth, moving carts of parts. Software dashboards are flashing green.
The system is consuming a massive amount of input and starting a massive amount of work, but it is finishing very little. We confuse local activity with system flow.
It reminds me of city planning. It's like having a beautiful, freshly paved 6-lane superhighway that suddenly funnels into a 1-lane dirt road over a bridge.
Oh, that's a great comparison.
Spending millions of taxpayer dollars to pave those 6 lanes perfectly smooth, or adding a 7th lane, doesn't get a single commuter to their destination across the bridge any faster. The bridge is the constraint. All the superhighway does is ensure that all the cars arrive at the traffic jam much quicker, where they sit idling, burning gas, and getting angry.
The highway analogy is perfect. And the fascinating thing is that this isn't just a conceptual philosophy. This traffic jam behavior is governed by absolute mathematical laws.
Really?
Yes. There is a specific formula that proves undeniably that dumping more work into a system without expanding the bottleneck doesn't increase output. It purely increases wait times.
Right. I don't just want to rely on analogies. Let's look at the actual physics of this. The sources introduce a concept called Little's Law.
Yes.
It's time to get a little bit nerdy and do some operational mathematics, but we will walk through it carefully because the implications are massive.
Little's Law is a foundational theorem in queuing theory. It was formalized by a professor named John D.C. Little at MIT in the early 1960s. He provided a mathematical proof for a fundamental underlying relationship between 3 specific variables in any stable system where things wait in line.
Okay, what is it?
The equation is extraordinarily simple on its face. Work in process equals throughput multiplied by cycle time. Or, as it's often written, WIP equals TH times CT.
Okay, let's define those 3 terms so we are completely clear. WIP, or work in process, is the average number of items currently sitting anywhere inside the system at a given time. It's the total inventory of unfinished stuff.
Exactly.
Throughput, or TH, is the average rate at which finished items are departing the system. It's the speed of output, like 10 parts per hour.
Yes.
And cycle time, or CT, is the average amount of time a single item spends inside the entire system, from the moment it arrives as raw material to the moment it leaves as a finished product.
Correct. It elegantly connects average inventory, average output rate, and average time. And the beautiful thing about Little's Law is that it is universally applicable. It does not care what the items are.
It could be anything.
It applies to cars on a highway, parts in a factory, customers in a bank line, or data packets in a server. The source material provides a highly relatable, non-industrial example to demonstrate how intuitive the math really is. Imagine a wine enthusiast named Caroline.
I like Caroline already. Let's say Caroline has a beautiful wooden wine rack in her cellar. The rack has a maximum capacity of 240 bottles. But she doesn't buy her wine all at once, and she doesn't drink it all at once.
Right. She notices that over the years, the rack is rarely completely full or completely empty. On average, if you walk down there on a random Tuesday, it stays about 2/3 full. So her average inventory, her work in process, is 160 bottles.
Okay, so WIP equals 160. And Caroline knows her own consumption habits. She looks at her credit card statements and realizes she buys, and eventually drinks, an average of 8 bottles a month. That is her output rate. So her throughput, her TH, is 96 bottles a year.
Now, Caroline is a casual enthusiast. She doesn't put little date tags on her bottles. She doesn't maintain a strict first-in, first-out digital tracking system. When she has guests over, she just wanders into the cellar and grabs whatever bottle pairs well with the pasta she's making.
But she's curious. She wants to know, mathematically, on average, how long is a bottle aging in her cellar before she pops the cork? What is her average cycle time?
Using Little's Law, it's basic algebra. We know that WIP equals throughput times cycle time. Therefore, if we want to isolate cycle time, we just rearrange the formula. Cycle time equals WIP divided by throughput.
So she takes her average inventory of 160 bottles, divides it by her annual throughput of 96 bottles a year, and the result is 1.67 years.
It's brilliant. Without having to meticulously track the journey of a single individual bottle, she knows with mathematical certainty that the average age of the wine she drinks is about 1 year and 8 months.
The variables are inextricably linked. We can apply the exact same logic to something much less enjoyable than a wine cellar: the modern corporate email inbox.
The ultimate site of unfinished work. Let's take a university student or a mid-level manager named Sue. Sue receives a steady stream of emails that require a thoughtful response. Let's say she's capable of processing and answering 50 emails a day.
That is her operational capacity, her throughput.
However, she struggles to keep up, and she notices that her inbox typically hovers around a backlog of 150 unanswered emails. That is her work in process.
So we use the rearranged formula. Cycle time equals WIP divided by throughput. 150 emails sitting in the queue divided by a processing rate of 50 emails a day. The math dictates that it takes Sue an average of 3 days to answer an email.
If you send her a message on Monday, you aren't getting a reply until Thursday.
Exactly. The physics of the queue dictate the delay. But wait a minute, let me play devil's advocate here. Because if I am an aggressive, ambitious manager, I look at that equation.
WIP equals throughput times cycle time.
Right, and I might draw a very dangerous conclusion. If I want to increase my throughput, like if I want to get more output, higher revenue, more finished products, mathematically, shouldn't I just shove more work in process into the system? If the left side of the equation, WIP, goes up, should the right side, throughput, go up to match it? My instinct is to release more raw materials, start more projects, get more things going.
And that is the exact logical trap that snares countless organizations. It assumes that the causality flows freely in both directions under all conditions.
It assumes the system has infinite capacity.
Exactly. But this is where we have to merge Little's law back with Goldratt's theory of constraints and introduce a crucial operational concept called critical WIP. Let's break that down. Remember the rusted link in the chain. Your system's throughput is ultimately capped by the physical reality of your bottleneck. A system can never output faster than its slowest step.
Right.
Critical WIP is defined as the absolute minimum exact amount of inventory required to keep that specific bottleneck running at 100% of its maximum capacity, with zero idle time, assuming a theoretically perfect system with no variability.
So to be clear, you do need some work in process. I mean, if WIP is 0, nothing is happening. If WIP is too low, the bottleneck might finish a part, look around for the next one, and have to wait.
Right, that's called starving the bottleneck, and that definitely drops your throughput.
Okay, so you need enough WIP to feed the constraint.
Correct. But, and this is the turning point, once you reach critical WIP, once your bottleneck is running at its absolute maximum capacity of, say, 10 parts an hour, it cannot go any faster. Throughput is now a locked static number.
Okay, I see where the math is going to break my brain.
So, if throughput is maxed out and locked, and the ambitious manager continues to shove more work and process into the front of the system, let's look at the equation. WIP equals TH times CT. If WIP is rising rapidly, but TH is frozen at its ceiling, what is the only variable left in the equation that mathematically must increase to keep the formula balanced?
Cycle time. The cycle time has to go up.
It is unavoidable. Adding more work into a system that is already constrained at its bottleneck does not increase the rate of output. It mathematically forces the average time it takes to complete anything to stretch out longer and longer.
Wow.
This leads to one of the most profound realizations in operations management. Inventory is not just an inanimate object taking up physical space on a factory floor. Inventory is time waiting to be experienced.
Inventory is time waiting to be experienced. That fundamentally changes how you view a backlog. A large queue isn't a sign of robust health. It is a guarantee of future delay.
Yes, exactly.
Let's ground this heavy math in a massive real-world example provided in the source material regarding project management. Think about a colossal capital project. Something like an onshore oil and gas field development.
The stakes in this example are incredibly high. We are talking about hundreds of millions of dollars of capital expenditure, massive supply chains, and intense pressure from shareholders to deliver return on capital.
So the business target for this new oil field is ambitious. They need to put 100 new producing wells online in a single calendar year. That is their required throughput.
Okay.
So 100 wells divided by 365 days means they need a throughput of approximately 0.274 wells completed per day. Now, based on geological surveying, drilling physics, and construction logistics, the engineering team knows that the cycle time, like the time from the moment they break ground and start drilling a well to the moment oil actually flows into the pipeline, is firmly established at 240 days.
So we apply the rearranged Little's law to find the critical WIP. If we want to achieve a throughput of 0.274 wells a day, and we know the cycle time is fixed at 240 days, We multiply them together. 0.274 times 240 equals roughly 66.
The required work in process is 66 wells.
Meaning, for this massive operation to perfectly hit its target of 100 wells a year at any given snapshot in time, the organization should have exactly 66 wells in some stage of progress.
Some are just being drilled, some are being piped, some are in final testing. 66 is the magic number.
Now enter human psychology and corporate pressure. What if the executive management team, looking at early delays or simply eager to show investors that they are aggressively getting things going, authorizes the drilling teams to start work on 80 wells simultaneously?
They have 80 wells actively chewing up dirt in the system. But the physics and the math of Little's law say they only needed 66 to hit their optimal flow.
Which means those extra 14 wells are entirely unnecessary work in process. Starting them does not miraculously increase the throughput capability of the specialized fracking crews or the pipeline welders who represent the system's bottlenecks.
So what are those 14 extra wells actually doing?
First, they are tying up staggering amounts of working capital. Millions of dollars are sunk into holes in the ground, generating zero return, completely illiquid. Second, and more destructively, because the company's finite resources, the heavy machinery, the specialized engineers, the project managers, must now be spread thinner across 80 active sites instead of 66, the bottleneck gets overwhelmed.
The math takes over.
Because WIP went up while capacity remains static, cycle time must expand. They have mathematically dragged out the completion time for every single well in the entire system.
But trying to do more, by being aggressive, they actively sabotage their own delivery dates. It is profoundly counterproductive.
It really is.
And there's another example in the sources, moving from a macro oil field down to a specific third-party welding fabricator that shows how this exact dynamic can spiral into a complete operational collapse.
The sources refer to it as the cycle time explosion. This explores the nonlinear relationship between utilization and wait time. This is what happens when you push a system's constraint not just to its limit, but beyond the threshold of reality.
Let's picture this third-party industrial fabricator. They're contracted to build large steel modules for a construction project. They have various stations, cutting, bending, assembling. But their clear system bottleneck is the final welding bay.
Okay, standard setup.
Let's say this welding bay, running perfectly with all its highly paid welders, has a maximum theoretical capacity of outputting 50 inches of finished weld per hour. Right now, the fabricator is managing their flow reasonably well. They have enough incoming work queued up to keep that welding bay at about 80% utilization.
Which, in the real world, sounds excellent. An 80% utilization rate on a constraint is generally considered highly efficient. It leaves a 20% buffer of protective capacity for things to go wrong.
But the upstream project manager, the client who is buying these modules, is behind schedule on their own macro project. Panic sets in. They decide they need to catch up, so they back a truck up to the fabricator and dump a massive new, unplanned batch of module orders onto the shop floor.
Oh, no.
They effectively force the fabricator to push that welding bay's utilization target past 85, 90, maybe even 95%. They demand maximum effort.
What that panicked project manager fails to understand is the mathematical nature of queues. Queue times do not scale linearly in a straight, predictable line. Because we do not live in a theoretical spreadsheet. We live in a physical world governed by natural variability.
Explain that variability. What goes wrong in a welding bay?
Everything. A welder needs to take a mandatory safety break. The automated welding machine needs a 15-minute recalibration. A batch of steel arrives with slightly higher carbon content and takes longer to heat. A complicated joint doesn't fit perfectly the first time and requires 5 minutes of grinding.
And in an 80% utilized system, that 20% protective capacity acts as a shock absorber. The system easily recovers from those minor hiccups.
Exactly. But at 95% utilization, at 95%, there is no shock absorber. Every single minor delay cascades into the next job. As utilization approaches 100%, the wait time in the queue doesn't just increase slightly, it increases exponentially. On a graph, the curve wait time is flat for a while, and then it suddenly goes straight up like a hockey stick. It approaches infinity.
So by shoving that massive extra batch of work into the shop to get it done faster, the client effectively breaks the system. The cycle time for the steel modules absolutely explodes, the queue stretches out the door, and the fabricator ends up catastrophically missing every single one of their promised delivery dates.
It is the brutal mathematical certainty of Little's law interacting with the reality of statistical variation. You simply cannot force a system to process faster than its constraint by suffocating it with an avalanche of unfinished work.
Okay, my head is spinning a bit from the math, but the takeaway is glaringly obvious. Hearing all of this, the hidden sunk costs of waiting, the dangerous illusion of local efficiency, the exponential delays and hockey stick graphs caused by overloading the bottleneck, I feel like I am ready to make a radical, sweeping operational pivot.
Uh-oh, here it comes.
I get it. The epiphany has arrived. All inventory is bad. Work in process is pure evil. If I am the CEO, I am going down to the floor tomorrow and implementing an absolute ruthless zero inventory policy. We are burning the buffers. We are emptying the factory floor. If it's not being worked on this very second, it goes in the trash.
And that, right there, is exactly the massive overcorrection that drives many well-intentioned organizations into complete operational paralysis.
Wait, really? After everything we just discussed?
Yes. Because Little's law is a descriptive mathematical reality, it tells you what is happening. But it is not a diagnostic root cause cure-all. You cannot just command the math to change by indict. We must apply incredible nuance here. Indiscriminately and blindly removing all buffers from a system can be just as destructive and just as careless as indiscriminately creating them in the first place.
Okay, that's it.
We must distinguish between the intentional and the unintentional.
So not every buffer is wrong. There are times when it is actually right and strategically sound to have a pile of unfinished work just sitting around.
We have to analyze the intent behind the accumulation. What is the operational purpose of a deliberate, intentional buffer? It exists to protect the flow of the entire system from the expected, normal variation we just talked about. It is the shock absorber.
Let's go back to Goldratt's chain analogy. If the bottleneck is the weakest link, and the system's total output is entirely dependent on that link, we want to make absolutely sure that the bottleneck is never, ever idle, right?
Right.
Because an hour of production lost at the bottleneck is an hour of production lost for the entire system forever.
Yeah.
You can't get it back.
Exactly. So a smart operations manager will place a small, highly calculated, closely monitored buffer of inventory directly in front of the bottleneck. This is strategic.
Okay, that makes sense.
It ensures that if an upstream machine breaks down for 20 minutes or a material handler is late returning from lunch, the bottleneck does not starve. The constraint can just reach into the planned buffer and keep working. That is purposeful inventory. It is an investment in operational insurance to guarantee the throughput of the entire system.
Okay, that makes perfect logical sense. It's a firewall against Murphy's Law. But what about the other kind? What about the unintentional buffers, the ones that just organically sprout up like weeds in the corners of the factory, the carts that sit there for 3 years under a faded yellow floor sign?
Right.
If they aren't protecting a constraint, what are they doing? What are they hiding?
That is the most critical investigative question a leader can ask. When an accumulation of inventory isn't planned, it is almost always acting as camouflage. Unintentional buffers conceal systemic instability and process failures. Because the piles of work isolate the workstations from each other, the upstream station doesn't feel the pain of the downstream station's failure.
Our sources provide a taxonomy of these failures. They list several specific conditions that these accidental buffers might be hiding. Let's run through them and really look at the mechanics of why they happen.
Okay.
First on the list, an unreliable handoff or missing information.
This is incredibly common, especially in complex manufacturing or engineering. The upstream machine or the upstream team completely finishes their physical or digital job. But they cannot pass the item to the downstream process because a critical piece of data is missing.
Like what?
The physical part is ready, but the engineering drawing is missing a crucial tolerance dimension, or the digital quality assurance approval hasn't cleared the software system.
So the physical part just sits on the trolley, perfectly machined, waiting for an email.
Yes. The material flow is blocked by a failure in the information flow.
The second condition the sources identify is rework and poor first-pass quality. This feels like a huge one.
It is massive. In this scenario, the item is built, it travels down the line, but it fails a quality inspection. The hole was drilled 2 millimeters too wide. Now, it cannot proceed, but the company doesn't want to throw away the expensive titanium, so it gets placed in a quarantine queue.
And it just sits there waiting for an engineering committee to figure out if it can be salvaged or rewelded or sold as scrap.
Precisely. To the untrained eye, that quarantine cart looks like standard inventory. But it is actually a physical manifestation of a broken quality control process upstream. The buffer is hiding the fact that the upstream machine is out of calibration.
The third condition is one driven by accounting logic again. Large batch policies.
This happens when the setup time for a machine is very long. If it takes 4 hours to change the tooling on a press, the manager decides it is too financially inefficient to set it up to stamp just one part. So they implement a policy. We only run this machine in batches of 50.
Which makes sense locally for that one machine's setup costs. But think about the parts. The first part in that batch of 50 might be stamped and ready to go in 10 minutes. But it cannot move downstream. It is held hostage.
Yeah, it has to sit on a cart and wait weeks for the other 49 parts to be processed before the whole batch is allowed to move forward. The policy artificially inflates the cycle time of every single item.
And finally, the most straightforward condition, an unavailable downstream process.
The next machine in the sequence is catastrophically broken. Or the specialized operator called in sick and there is no cross-trained backup. Or the system is just completely out of balance, as we discussed with the fast machine feeding the slow inspection station.
In all of these scenarios, missing data, quality failures, batching rules, broken machines, the inventory itself is completely mute. The beautifully machined titanium component cannot raise its hand, speak up, and explain to the plant manager which of these conditions applies.
It can only sit there on the trolley with remarkable professionalism.
Right. It is entirely up to the managers to recognize the cue as a symptom, investigate the root cause, and fix the system.
Therefore, the objective of lean management is not zero inventory. The objective is purposeful inventory and observable flow.
Purposeful inventory and observable flow. We want to be able to see the work moving at a predictable rhythm. And if that flow stops, we do not want it hidden in a massive pile.
Exactly. We want the stoppage to be immediately visible so we can ask exactly why it stopped rather than just accepting the stagnant cart as a normal part of the factory scenery.
Which brings us to a fascinating, almost anthropological evolution of these stalled components. Let's talk about the administrative afterlife.
This is where human psychology, corporate culture, and operations science violently intersect.
We touched on this briefly when we talked about the painted square on the floor, but it is so prevalent in corporate life it deserves its own deep dive. When a piece of unfinished work persists in a system for a long enough time, it begins to attract its own bureaucratic ecosystem. It is exactly like a coral reef forming on a sunken ship.
That is a brilliant visual metaphor. Nature abhors a vacuum, but corporate structures absolutely abhor unmanaged anomalies. If something exists, it must be governed.
So let's trace the life cycle of this reef. First, the stalled work gets a label. The cart receives a sign that says temporary WIP. Then, because the cart is not moving and people need to know where it is, it gets a tracker. A line item on a spreadsheet, or a physical Kanban card attached to a clipboard.
Then, because that tracker needs to be updated weekly to report to upper management, the stalled work acquires an owner.
Oh, definitely.
The company assigns an expediter or a junior project manager whose entire job is to monitor the things that are not moving.
And because there is now a project manager assigned, that manager needs to demonstrate their activity. So they schedule a recurring Thursday morning review meeting, inviting 3 different department heads to discuss the status of the tracker that governs the label on the work that still isn't moving.
The queue was not completed, but its governance model was.
That observation is so cynical but so painfully true. The queue was not completed, but its governance model was. We build an entire shadow organization just to monitor our own stalled progress.
And we must recognize that this is not usually driven by malice or sheer incompetence. It is a natural human adaptation. Conscientious employees build processes around persistent constraints because they feel a deep responsibility that the work must be managed somehow.
Right.
But the tragic irony of this corporate instinct is that a successful administrative workaround actually makes the underlying obstructing condition much less visible.
Because the pain is localized to the meeting, not the factory floor.
Exactly. The organization becomes incredibly, remarkably excellent at accounting for the waiting. The waiting begins to look highly managed, highly professionalized. The spreadsheets are color-coded, but the root cause is never addressed, and the work itself is still entirely unfinished.
It's so true. I have sat in those exact meetings. We spent a full hour in a conference room discussing why a specific project was delayed. We interrogated the timeline, We updated the Gantt chart, we adjusted the milestones, and everyone walked out of that room feeling very productive and sweaty.
I'm sure they did.
And yet the physical project was exactly as unfinished as it was an hour ago. We moved the administration, we didn't move the work. Which is a perfect segue into how this entire philosophy applies to so many of you listening right now.
Because we have been talking extensively about titanium components, welding bays, and oil rigs, but these physical principles apply perfectly without alteration to the modern, purely digital workplace. We need to talk about knowledge work.
The underlying physics of flow and the mathematical reality of Little's law do not care if the work in process is made of machined aluminum or compiled lines of software code. The patterns of constraint are identical.
In knowledge work, we are constantly dealing with the exact same phenomenon. Committed effort and sunk cost, just sitting in a queue, awaiting completion.
So let's map this out clearly. Let's translate the factory to the office. In a manufacturing plant, the unfinished work is a partially machined component on a cart. In an IT department or a software company, what is it?
In software, the most common form of stalled WIP is code that has been written by a developer but is sitting in a queue awaiting peer review or testing. The developer has already spent their highly compensated hours writing the feature. The financial cost is completely sunk.
Yeah.
But until that code is reviewed, approved, tested, and finally merged into the live production environment, it delivers absolutely zero value to the end user.
You're just sitting in a digital staging area.
It is. But in software, it's actually worse than a physical part. A physical part on a cart just gathers dust. But software code decays.
Decays.
Yes. A stalled code change is essentially postponed feedback. The longer that code sits unmerged in a repository, the higher the mathematical probability that another developer will change a fundamental part of the system, causing a massive merge conflict. When they finally go to integrate the stalled code, it breaks the application, creating massive amounts of rework that wouldn't have existed if the code had flowed smoothly.
Okay, what about finance or administrative services?
Consider an invoice that has been fully prepared by the billing department, but is awaiting a final executive signature for approval. The actual service has been rendered to the client, the administrative labor of generating the bill is finished, all the effort is expended.
Right.
But an unsigned invoice sitting in an email inbox is simply delayed cash collection. It is literal liquid capital trapped inside an administrative queue.
And my personal favorite example of knowledge work, WIP, because it absolutely plagues every corporate environment on Earth, from startups to Fortune 500s. Decisions that are thoroughly discussed but carefully structurally protected from actual conclusion.
That is the ultimate invisible work in process. A systemic problem is identified. Data is gathered by analysts. A high-level meeting is convened. But because of political fear or a desire for absolute consensus, no firm decision is finalized. The decision itself becomes an unresolved item in the organizational system.
And what happens to an unresolved decision?
It becomes 5 more meetings performing a live, agonizing reconstruction of the unresolved decision.
Precisely. Because human memory fades, you have to relitigate the entire context every single time you meet. Remind us what we discussed last month. It consumes massive amounts of executive cognitive capacity, it burns highly paid calendar hours, but the actual throughput of finished, executed decisions remains at absolute zero.
So, whether you are managing a heavy industrial factory floor, leading a 2-week software sprint using Jira tickets, or sitting in an executive boardroom trying to steer a company, how do you actually fix this? When you walk past idle work, whether it's a physical cart blocking an aisle or a digital ticket that hasn't moved in a month, what should you do?
The instinct of most managers is usually to look at the idle resource and ask a utilization question. They ask, why isn't this machine running? Or why isn't that employee busy typing?
But based on everything we know about local efficiency and constraints, that is the wrong question. It focuses entirely on keeping the links of the chain busy rather than increasing the strength of the chain. Instead, we need to ask investigative questions that focus entirely on completion and system flow.
The sources give us a fantastic practical list of better questions to investigate when we encounter stalled work. First question, what customer outcome does this specific item ultimately support?
This forces you to look past the item itself and remind yourself of the actual value that is currently being delayed. It re-anchors the work to the outside world.
Second question, which costs have already been committed to this item?
This breaks the illusion that the cart is free inventory. It demands that you understand the financial weight, the trapped capital, and the sunk labor currently sitting in the queue.
And third, perhaps the most revealing and diagnostic question of all, was this item released into the system because the system was actually ready to finish it? or just because the upstream resource was available to start it?
That question strikes at the absolute crux of overproduction. It demands honesty from leadership. Did we start this massive new project because we actually had the downstream capacity to deliver it all the way to the customer? Or did we start it simply to keep a development team busy, to keep a machine running, knowing full well that it would inevitably hit our bottleneck and stall out?
It is about fundamentally shifting the managerial focus from the illusion of keeping everyone perpetually busy to the reality of helping the system actually deliver finished value.
It is a profound structural shift in operational philosophy. It requires abandoning the comfort of visible motion for the harder discipline of actual progress.
Let's bring it all back to where we started this journey. We are back on the concrete floor of that factory, standing under the bright lights, looking down at that immaculate, highly processed component resting silently on its temporary cart. I want you, the listener, to think about your own world, your own daily reality, your own digital or physical workspace. What has your organization already paid to start, but has not yet created the conditions to finish?
Right.
So the most expensive part may not be the part with the highest price.
It may be the one carrying almost all its cost while still delivering none of its intended purpose.
Fully paid for, completely unfinished.